Hey there everybody, welcome back. So this example will be finding the net torque on an object and ultimately finding the net angular acceleration. So what we have here is a solid cylinder of radius capital R, okay, and mass we'll call capital M eventually, okay. It's subjected to four forces, F1 through 4, and they're oriented as shown in the picture, right? F1 is tangent to the cylinder's surface. So in other words, the distance or the r vector that goes from the axis to where the force is applied is perpendicular to F1. Okay? F2 is the same thing, right? But kind of in the other direction. So F1 would rotate it counterclockwise. F2, if that were the only force, would rotate the cylinder clockwise. All right, so they're kind of competing forces that result in kind of competing torques. F3, as shown here, it's perpendicular with its own lever arm, right? Its own r vector, and it's perpendicular to that, oriented as shown, right, straight down. And F4 is actually parallel with its r vector, right there. That's in the same direction as r. So thinking ahead, r cross f for F4, that would not provide a torque, right? Because that angle in between it would be 0. So let's write out the net torque equation and see what we got. Net torques. All right, that means we have, well, 4 forces results in 4 torques. So let's just go ahead and do all this. So we have R cross F1 as 1 torque. And I'm just going to add them all up for right now. R cross F2, and then R cross F3, then R cross F4. Right? And just like back in chapters 5 and 6, for a net force, we had that equaling mass times the net acceleration. In chapter 10, when we have a net torque, it's the moment of inertia times the alpha, right? Moment of inertia is the analog, is the chapter 10 analog to mass, right? It's the object's resistance to change in its rotation. And then alpha is the chapter 10 analog to A. So this is one giant Newton's second law for rotation. Okay? So let's go through it and write down each of the torques here. So we mentioned F1, which, by the way, we have the magnitudes of all 4 forces and the magnitude of both lowercase and capital R. So we can write in the numbers here if we wanted to. So let's see, F1 has a torque of capital R times F1. These are both the magnitudes now. And then sine of the angle in between those, well, that was 90, right? So sine 90. Then, is that positive or negative torque? Because we need to specify that now. F1, like I mentioned earlier, would rotate this cylinder. If it were the only force, it would rotate it counterclockwise. So that means, by convention, counterclockwise results in positive torque, clockwise results in negative torque. So that means this is positive, right there. For the second term, F2, that would rotate it clockwise if it were the only force on it. So that means that's a negative. That magnitude, right, of R is capital, and F2, and then sine of the angle in between those two, again, is 90. Okay. Now for force 3, the magnitude of that lever arm, again, it would be negative torque, would rotate it clockwise. Lowercase r, F3, and then sine of 90 again. Thankfully, these are easy so far. And lastly, F4, that's parallel to R, right there. So sine of 0 is, well, 0. So if you want to do that like this, sine of 0, that whole thing goes away, okay? And then we have I alpha at the end. And so this entire problem, we're trying to solve for the value of alpha, right? So let's keep reducing it down. So we have, let's see, F1, we know the magnitudes there, F2, F3, F4, right? We know the magnitude of capital R and lowercase r. And so, yeah, let's do it like this. F1 sine 90 is 1 minus R F2 minus lowercase r F3, right? Actually, let me put I alpha on the left here. And really, the rest of the problem is algebra, right? This first line and this second line is really physics, right? That's the new physics from chapter 10. And once you get that, then it's just algebra, right? The problem doesn't say the value for a moment of inertia in this case, but we can see it's a solid cylinder. So looking back to that table of moments of inertia values, we can see that I for a solid cylinder is 1/2 mr squared. And by the way, this r is the maximum radius, right? So that means I'm going to do it over here. We have 1/2 the mass of that cylinder times the radius of the cylinder times alpha. We know the mass. The problem tells us mass of 2 kilograms, and capital R is the same as what we have in the torques. Right? So now we can basically plug everything in. So I'm going to solve for alpha, and that means I'm dividing by what's in parentheses. So dividing by 1/2 mr squared means we have a 2 on top. And then I'm going to go ahead and plug in, well, yeah, we'll plug in numbers. So R is 0.12. Let's do it that way. F1 has a magnitude of 6 newtons minus capital R 0.12. F2 has a magnitude of 4. Then the third term, lowercase r 0.05 times the magnitude of F3, which was 2. And that's all on top, divided by mr squared, so the mass is 2, times r squared, 0.12 quantity squared. And if we evaluate this, we should get 9.72 radians per second squared. Yep. Whoops. 9.72 radians per second squared. SI units in equals SI units out. There we go. Is this positive or negative? Right? We've talked about positive or negative torques, whether they're, let's see, counterclockwise or clockwise, respectively. The same thing applies for angular accelerations. So we end up getting a positive value, which means that it will be clockwise. Right? Clockwise direction. Sorry, I said something different and wrote something different. I was like, positive torque means it'll be a counterclockwise direction. Oh boy. Okay, that's it, right? That's basically how we do a net torque problem, Newton's second law for rotation. We have Net torques, we have 1, 2, 3, 4 torques. Add them up, keeping in mind the signs for direction. And then we set that equal to I alpha, right? And then we just solved for alpha. All right. Thanks for watching.